Hey everyone, we're picking up with this example where we left off. So now we're going to start talking about the calculus for parametric curves. Um, so once again, let's consider the fact that we have the problems x equals f of t and y equals g of t on some sort of interval. The question that we're asked is how do we compute dy by dx? Remember that that is the slope of the curve at a given point. So first of all, what I'm going to do is I'm going to note that if we have a function, we can write that y is equal to y of x, but x is really just a function of t, so we could write y of x of t, and now it kind of looks like a composition of functions. We have an outermost function y and an innermost function x of t. All right. So the chain rule would ultimately tell us that if we wanted to compute something like dy by dt, then this would be equal to dy by dx times dx by dt. One way to kind of think about it, even though this isn't technically correct, is that the dx's here cancel out, and what you're really left with is just dy over dt. Dy over dt. And yeah, then if we really care about finding dy by dx, remember that's the whole point, is we can divide both sides by dx by dt. So dy by dx is equal to dy by dt divided by dx by dt. And hopefully this is a fairly easy thing to remember. The basic idea is that dy over dx is equal to the derivative of y divided by the derivative of x. And so this should be the thing that you guys memorize. Oh, this is going to do that thing. No? Okay. Yeah, that works. And we could also rewrite this as g prime of t over f prime of t if we once again consider that x is equal to f of t and y is equal to g of t. And basically that's what it says here in this theorem. It's that the derivative dy by dx, which gives the slope at any given point, can be calculated using parametric equations as gy or g prime of t over f prime of t, provided that f prime of t is not equal to 0. All right, so this is our first foray into calculus in parametric curves, and we're just calculating the slope of our curve at a given point. So let's examine this. First, let's start by considering the parametric equations given by x of t and y equals 2 root t for t non-negative. We're going to describe the curve and find any points at which the curve has a horizontal or a vertical tangent line. All right, so first thing to note is that a horizontal tangent line occurs when the numerator of dy by dx is equal to 0. Let me say is equal to 0. And the denominator of dy by dx is not equal to 0. It's very important that we also meet the second condition. Similarly, a vertical tangent line occurs when the denominator of dy by dx is not equal to 0, and the numerator, sorry, this is equal to 0, and the numerator of dy by dx is not equal to 0. All right, and this is not the same thing as saying dy by dt equals 0, and dx by dt is not equal to 0. It is not the same thing as saying that, and we will see that here in this example. All right, so let's go ahead and calculate dy by dx. So dy by dx is equal to dy by dt divided by dx by dt. Remember the mnemonic. And dy by dt is the derivative of our y function with respect to t. And so that's just going to be 1 over root t. And the derivative of x with respect to t, this function, of course, derivative of which is just 1. So this is just 1 over root t. All right. So one thing you will notice is that dy by dt and dx by dt, neither of those things are ever 0. This function cannot be 0 on any value for t, and this function is 1, which is obviously not 0. So it is definitely not the same thing to say that dy by dt equals 0. What we're really looking for is the fraction that is created after we have computed dy by dx. So the numerator of this dy by dx is 1, and that can never be 0, so therefore there is never a horizontal tangent line. So no horizontal tangent line. That's what this is, a horizontal tangent line, and then this is a vertical tangent line. However, at t equals 0, the denominator is equal to 0, and the numerator is not equal to 0. So we actually do satisfy both criteria for the vertical tangent line at t equals 0. So a vertical tangent line occurs at t equals 0. So you'll notice that this is a little bit different than whenever we were considering vertical tangent lines and horizontal tangent lines in Calculus 1. In this particular circumstance, rather than identifying the x and y coordinates where that horizontal and vertical tangent line will occur, we identify the t value where that will occur. If we wanted to determine the x and y coordinates, all we would simply need to do is plug this value for t into the x and y coordinates here. So let me just go ahead and write that down. So this means at the xy coordinate 0, 0. All right. And finally, we should also attempt to describe this curve. The idea here is that since x is equal to t, we could eliminate this parameter and just throw x right there, and we would get y equals 2 root x. So the curve is y equals 2 root x. And this is probably sufficient. We could further say that this is twice the standard square root function. I don't know. All right, and so we have described our function, we have described our curve. All right, so let's take a look at the second example. It's a little bit trickier. We're going to consider finding the dy by dx for this guy. Same prompt, describe the curve, find any points at which the curve is horizontal or vertical tangent line. So let's try. If x is equal to 4 cosine of t and y is equal to 16 sine of t, and t ranges from 0 to 2 pi, then dy by dx once again, is dy by dt divided by dx by dt. Dy by dt is just 16 cosine of t, and dx by dt is negative 4 sine of t. We can simplify this to be negative 4 times cosine of t over sine of t. Let me actually write the negative 4 in the numerator. I could write this as cotangent of t. I would argue that that actually makes things more confusing because I'm going to end up explaining this in terms of sine and cosine anyway. So we're just going to leave it like this. Alright, so the thing that we should look at now is considering the horizontal and vertical tangent lines. So horizontal tangent lines occur whenever the numerator is 0 and the denominator is non-zero. So when cosine of t equals 0 and sine of t is not equal to 0. So what t values allow that to occur? So this means that we have horizontal tangent lines. Well, let's think about the zeros for cosine of t. So certainly at t equals pi over 2, that'll happen. And also at 3 pi over 2, that will occur as well. And let's check that sine of t is not 0 at both of those. Sine of pi over 2 is 1. Sine of 3 pi over 2 is negative 1, so we are good. Both of those work. A vertical tangent line occurs when sine of t equals 0 and cosine of t is non-zero. Alright, so sine of t is equal to 0 at 0 pi, and since 2 pi is included as well, we will go ahead and include that point, 0 pi and 2 pi, and double checking, making sure that cosine of t is not 0 at any of those. Cosine of 0 is 1, cosine of pi is negative 1, cosine of 2 pi is 1. We are good. All of those work out. And so these are our horizontal and vertical tangent line points. We could similarly associate a xy coordinate with each one of these. For brevity, we will not do that here. Alright, we want to describe this curve and any points at which the curve has a horizontal or a vertical tangent line. The description of this curve, this is actually an ellipse, and perhaps it's difficult to see that at the moment. Notice that since we have x equals 4 cosine of t and y equals 16 sine of t, that seems very similar to a circle, but since we have a 4 and a 16, which are, of course, different numbers, it is not quite a circle, but actually an oval, an ellipse. So the curve is an ellipse. The larger axis, the longer axis through the circle, is going to be the one that corresponds with this equation. So you'll notice that we actually draw this on the next page. This is an ellipse with the longer axis in the y direction, hence the fact that we have the y equation with the larger number in front of sine. And so the longer axis occurs in the vertical direction and the shorter axis occurs in the horizontal direction. And in particular, the axis length, the radius length, the major radius is going to be 16, and the minor radius will be 4. All right. And yeah. And we also notice that at t equals pi over 2 and 3 pi over 2, there is indeed a horizontal tangent line. So here is t equals pi over 2, here is t equals 3 pi over 2, and there's a vertical tangent line at 0, pi, and 2 pi. And you can also calculate the slope for any other point t. So if we wanted to know the slope at this point, at pi over 4, all we would have to do is plug pi over 4 into this function. This graph over here on the left is the graph for the first function that we did. You'll remember that there were no horizontal tangent lines, but there was a vertical one right here at t equals 0. And it does look to appear that way in this function as well. All right, great. Next, let's consider this idea of arc length for parametric curves. So in section 6.5, way back when we were actually in class and studying this stuff, we presented a formula for finding the arc length of curves. That formula was this guy. It was the integral from a to b of the square root of 1 plus f prime of x squared dx. The formula for parametric curves is actually quite similar. It's going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared dt. All right, and so this is something worth memorizing. Make sure that you have this idea under your belt. And one thing to note here is that the a and b for this function up here correspond to x values. So we would say, for example, 1 less than x less than or equal to 3. And then we would compute the arc length based off of these numbers. In this function, the a and the b correspond to bounds for t. So we will give you bounds for t, and then you will plug those in here. One thing to note is that most arc length integrals are really difficult to calculate exactly. In this section, we're only going to present values for which it is easy to compute such integrals. All right? So if you find yourself computing something that seems impossible, you've probably made an error somewhere in your calculations. So let's give an example a shot. We're going to prove that the circumference of a circle of radius r is 2 pi times the radius, or in other words, pi times the diameter. All right, so let's remember that a circle has the equations x equals r cosine t and y equals r sine of t. All right, and it's important to note what the bounds for t are that generate this circle exactly once. One thing that I didn't specify earlier that I wanted to, let's go back to our circle. Whenever we were discussing this parametric circle, we said that the bounds for the circle were 0 to 2 pi. If we were to consider the bounds from 0 to pi, then it would generate this part of the curve. If we were to generate the curve from 0 to 3 pi over 2, it would generate this part of the curve. If we were to go from 0 to 4 pi, then what it would do is it would actually generate this entire circle and then loop back again. We would have generated the circle twice. We would have looped back over ourselves one extra time. And so it is important that whenever we are doing these sorts of calculations, that we do not overlap our current function. We must trace the curve exactly once. All right, and so whenever we are doing this calculus stuff, that is a important thing to keep in mind. All right, so the integral then is the integral from 0, so let me write out that the bounds for t are 0 to 2 pi. And the function was the square root of f prime of t squared plus g prime of t squared dt. All right, f, remember, is the function associated with x. G is the function associated with y. And so let's call this thing L for arc length. So it's the integral from 0 to 2 pi square root. The derivative of f is just negative r sine of t squared. And the derivative of g is r cosine of t squared dt. All right, and so then you get a square root. All right, and now if you square the first piece, you would just get r squared sine squared of t. The negative sign goes away. Second piece will be r squared cosine squared of t dt. All right, and then what you might notice here is we can factor out that r squared. So we get the square root of r squared times sine squared of t plus cosine squared of t. And what do you know? Cosine squared of t plus sine squared of t is just 1. So this whole thing just disappears. Integral 0 to 2 pi. We are just left with the square root of r squared dt. All right, so what is the square root of r squared? Think about it. If you said r, you are wrong in general. This is technically the absolute value of r. In this particular example, we may also write that this is equal to the integral from 0 to 2 pi of just r. We can get rid of the absolute values. The reason we can get rid of those absolute values is because we assume that r is positive. We assume that r is greater than 0, which means, let me actually write it out. This means that the absolute value of r, of course, is equal to just r. All right. And so that's how we do this step. And whenever we integrate this, finally we're able to, we get RT evaluated from 0 to 2 pi. And whenever we plug in for t, we get just 2 pi r, which is exactly what we wanted to get. And so we've done it. We have shown that the circumference of a circle of radius r is 2 pi r. So this is another party trick that you guys can show all of your friends. You know how to compute the circumference of a circle of radius r. Just throw out your handy-dandy arc length integral for parametric curves and prove it in just a minute or two. Fun time. All right, so there's also a couple other uses for parametric equations. One use is to find the area underneath curves. The equation that finds the area underneath a curve is this guy. It is the integral from a to b of f prime of t g of t dt, where t is between a and b, that's the positive orientation, or perhaps b is less than or equal to t, which is less than or equal to a, that would be the negative orientation. This would actually generate the negative answer of what you're looking for. All right, and once again, we have to note that the parametric equation should trace out the curve exactly once. If it traces it out more than once, then we will get a different answer. We can also calculate surface area. And the basic idea is that we assume that f of t is non-negative on our interval. Then the equation for the area of the surface when we revolve around the y-axis, so this brings us all the way back to chapter 6 whenever we're talking about surfaces of revolution. The equation that calculates that guy is the integral from a to b of 2 pi f of t times this integral. This is going to feel very similar to what we did whenever we studied surface area, because previously we just had x, and then we would say 1 plus f prime of x squared, and we would go from here. And you'll notice this is basically the same idea. We have this arc length square root that's included, and then this is basically x, and so this is the same general idea, just with parametric equations now. Similarly, if g of t is non-negative, then we can figure out the surface area whenever we revolve around the x-axis using this guy. All right, we won't actually do an example of surface area here in the notes because I think the idea is fairly straightforward. All you have to do is plug in stuff into this equation. But I do want to do one example for this area function because it includes a particular curve that is interesting. And so in particular, we're going to consider the graph of a cycloid. So what we're going to do is we're going to find the area under one arch of the cycloid represented by these equations. So a cycloid, by definition, is the curve that is generated by these equations. All right, it must be, well, I don't know if I want to say must be, but the easiest way to represent a cycloid is with parametric equations. All right, so the picture for such a cycloid looks like this. Basically, it just kind of bounces off the x-axis like that. There is a physical interpretation of this. It has to deal with how a dot on a wheel, whenever you rotate this thing, is going to move whenever the wheel moves. Perhaps I shouldn't have done this with a laser pointer. And so the path that is traced out with that dot will be the graph of the cycloid. Anyway, we just need to calculate the area under one arch of the cycloid. So the important thing to discover here is where that arch, what the bounds for t need to be. So clearly, we can see that the arch of the cycloid occurs or starts whenever y is equal to 0 and y is equal to 0 here. So the question we should ask ourselves is, when is this function equal to 0? That will tell us the start and the end for our cycloid. Well, certainly, it is y is equal to 0 at t equals 0, because whenever you plug in t equals 0 right here, you would get 1 minus 1, which is, of course, 0. And this doesn't happen again until 2 pi. And so the bounds for us are 0 to 2 pi. Alternatively, you can just look at the picture and notice that this occurs at 2 pi. All right, so or I guess I shouldn't circle this 2 pi, because this 2 pi is with respect to x. It's at this 2 pi that you should note. All right, anyway, we are going to find the area. So the area underneath one arch is going to be the integral from 0 to 2 pi of f prime of t times g of t dt. And recall that x is f of t and y is g of t. All right, so plugging this in, the derivative of f of t is just 1 minus cosine of t, and g of t is just 1 minus cosine of t. All right, so we're going to need to expand this in order to calculate it. So we get 1 minus 2 cosine t plus cosine squared of t dt. If you remember back to trig integration, so I guess there is a small thing that you should recall from previous sections. This cosine squared of t can be rewritten specifically as 1 plus cosine of 2t all divided by 2. We can break up that fraction into a 1/2 and a cosine of 2t over 2. This will give us the integral from 0 to 2 pi of, so now 1 plus 1/2 is 3/2 minus 2 cosine of 2 plus cosine of 2t over 2 dt. And now finally we can integrate this. The integral of 3/2, of course, is 3/2 t. The integral of negative 2 cosine of t is negative 2 sine of t. The integral of cosine of 2t over 2, we have to end up dividing by another 2, and so we're going to get sine of 2t all over 4. This whole thing is evaluated from 0 to 2 pi. And if we plug this in, then we are going to get 3/2 times 2 pi minus, well, 2 sine of 2 pi is just 0. Sine of 4 pi is 0, so that's all 0. So now, let's see, did I make a mistake? I made a mistake in my notes. Okay. All right, so we're good. We're good here. Right. So now, if we plug in 0, then all of these values will be 0, and we just get 3 pi. All right, and so our answer is that there are 3 pi units of area underneath this first arch of the cycloid. So that's this thing. All right, and that's all I've got for you guys for today. This is an introduction to parametric curves. See me back next time for section 12.2. All right, talk to you later.